Welcome to our NLP class. This is part 18. In this class, we are going to learn about two more mathematical terms, eigenvalue and eigenvector. These are very important terminology in PCA model. So, we will see what is these mathematical terms are. Let us assume again the mapping function f of x, which actually maps my input space into an output space. Here I define my input space in a 2D plane, which is described by x and y's. And there are set of points on this plane. These points I can call it as A1, A2, A3, etc. And this f of that mapping function f of x transfers these points on xy plane into a new plane, which is called as x1, that is x prime, and x prime and y prime. And these points are mapped in a new plane as b1, b2, b3, etc., bn. So, I call this function mapping function as a linear transformation function which linearly transform my input space into an output space. So, let us assume this x1, y1, let us assume one point from this input space, this A1, which is described by x1 and y1. So, how I can compute this x1 prime and y1 prime, which is b1 in this new plane. This conversion is happening inside this f of x using a linear vector. This is described as, let us assume this x1 prime is equal to some u1 of x1 and u2 of xy1 and x, yeah. So, now we see that vector u1 and u2, and let us assume that another point y1, how that y1 is being mapped. Y1 prime is mapped by v1 of x1 and v2 of y1. Here we see another vector b1 and v2, and using these two vectors I mapped a1 as in b1 here. So, let us assume that I have my a1 in the input plane. Here is my a1, and using this vector u1 and u2, and I transform this as b1 here. And again there is another point, maybe let us assume that there is another point here, this is an a2, and which is mapping on this new plane, here is b2. So, these are my input vector, these are my output vector. Here using these vectors, we can transform these points into my new plane x11, y1 plane. So, these vectors are used for this f of x to transform the input space. So, the mapping can happen in any direction from a1 to b1, but for particular kind of vector, this a1 and b1 is on the same direction. It is the direction is not getting changed, only the magnitude got changed. So, the stretching, the a1 is stretched by some factor, we called it as lambda, and converted into b1. This magnitude of stretch is called as eigenvalue. Maybe lambda 1 is an eigenvalue for this vector u1 and u2. We can call this vector u1 and u2 as eigenvector. And for 2D plane, this is the 2D plane, it has two axes x and y. Here we have axis x prime and y prime. So, for 2D vectors, we do have two eigenvalues and two eigenvectors. There is another eigenvector which is v1 and v2 and with eigenvalue lambda 2. This is another new set. So, these two eigenvectors and eigenvalues will just transform into new space without changing the direction. Only the magnitude will get changed. But interestingly, these two eigenvectors are orthogonal to each other. So, here when you look at the new space, this will be orthogonal. So, let us see on our classical example. There is a house here. And how will I capture this information from my house? Let us assume that this is in 2D plane and I keep my camera here and take a picture, and this is one view, the front view, and I keep again the camera just that orthogonal to my first view, this front view. These two views are orthogonal to each other, and I have another view. This is side view. I call this as an V1 V2 and I call this as an U1 U2. Now, do you understand what these vectors means? Just capturing the information in particular direction, and it captures maximum information from this view, and again it captures the remaining rest of the information from the second view, and using these vectors u1 u2 and v1 v2, and the magnitude of this information captured on each orthogonal space is called as eigenvalue, lambda 1 lambda 2. So, now we have our in our 2D plane we can see this information, and another plane you can see this information. So, now with the help of eigenvalue and eigenvector, we can capture that information from this input space into our output space. This is the use of this eigenvalue and eigenvector. Interestingly, this so we will see with an example, and I will explain you how it works. So, let us assume there is an input vector, that input matrix 9 4 4 3. Now, for this input vector, how would I find out my lambda, that is eigenvalues and eigenvector v's? So, there is a formula to calculate. We will see that formula in our next class, how that formula is being captured, and we will see just the formula and how we calculate eigenvalue and eigenvector here. So, this is my input matrix, and then when I multiplied this matrix with my eigenvector v, I will end up with having the same vector which is stretched by the magnitude of lambda v. This is the formula. So, by solving this equation, I can calculate my eigenvector, I can find out my eigenvector, and I can find out my eigenvalue. This is a two-dimensional matrix. For two-dimensional matrix, I can find out two eigenvectors u1, u2 I can find out two eigenvectors, u1 maybe v1 and u2 v2 and also lambda 1 lambda 2. So, if it is a 3-dimensional matrix, then it would get increased, that u1 v1 and maybe w1 u2 v2 w2 and lambda 1 lambda 2 lambda 3. And you know that what these vectors means and what this lambdas means. Lambda is that magnitude of transformation, and the vectors, eigenvectors are the direction of change. Now, we will see the simple math how to calculate the eigenvalue for this input matrix 9 4 4 3. And since this is a symmetrical matrix means this values are same above and below the diagonal values. This is interestingly our eigen that covariance matrix is also an eigen symmetrical matrix. So, for any that symmetrical matrix, we will be able to calculate eigenvalue and eigenvectors. So, we will see how we can calculate eigenvalue for this matrix. So, eigenvalue for this matrix is calculated by just by having our this matrix, just convert this convenient polynomial matrix x minus 9, here x minus 3, and change the direction of the remaining numbers minus 4 and minus 4. For this one, calculate the determinant of this matrix. Then we can calculate the eigenvalue lambda x minus 9, x minus 3, and then minus 4 into minus 4. Then I would expand this values x square minus 3x minus 9x 21 minus 16, x squared minus 12x minus 11 equal to 0. Find out the roots of this quadratic equation. We will have x1 minus 11 and x1 minus 1, and here my lambda 1 is 11 and lambda 2 is 1. These are the eigenvalues. And how do I calculate my eigenvector? That again we will see. My input matrix is 9 4 4 3, and the equation I explained is that input matrix which is multiplied by my eigenvector, which is equal to multiplying by a scalar which is eigenvalue that with my eigenvector. This is the equation, and we can just simplify this equation and find out our eigenvector. Just 9 4 4 3. Let's assume this is v minus lambda, multiply this with my unit vector to convert this into a matrix, minus equal to 0 0. Now, I can solve this equation and find out my eigenvector. I know that eigenvalues, just substitute this eigenvalue 11, 9 4 4 3 minus 11 0 0 11, and then it is multiplied by my v, maybe I will call this as v1. How would I represent? Maybe I will represent this v as u1 v1, and then my 0 0. Simplify this equation 9 minus 11 to 4, 4, 8 minus 8, and u1 v1 0, 0. Then simplify this equation. You will get two polynomial equations, minus 2u1 4v1 equal to 0, 4u1 minus 8v1 equal to 0, and by simplifying this equation I will end up with my eigenvector u1 v1 equal to 2 and 1. Similarly, by substituting my lambda equal to 1, I can calculate another eigenvector u2 v2, which will be minus 1 and 2. When you look at these eigenvectors u1 v1 and u2 v2, these are orthogonal to each other, and I know my eigenvalue, which is lambda 1 equal to 11 and lambda 2 equal to 1. This is my linear mapping function f of x. The f of x can use this information and convert any values from my input space x and y into my new space, which is x prime and y prime. Now we know what is eigenvalue and what is eigenvector, how we can compute eigenvector and eigenvalue. These two definitions are very important for defining our principal component analysis model. So we will see how the principal component analysis model is defined using these three terms. One is covariance matrix, which is sigma, and my eigenvalues lambda, and my eigenvectors v. Using these three terms, how we can define our principal component analysis model. We will see that in our next class. Bye. Thank you.